Good afternoon. Welcome to our last lesson of this year. Please be sure to listen all the way to the very end of the lesson because there'll be some instructions and things. So we're going to finish up. This might be a little bit longer than normal due to the fact that I'm going to try and put 3 lessons into one. It shouldn't be 3 times as long as normal, but it might be a little bit longer. I'll try to compress a lot of stuff. So we've been studying radiation and radioactivity and how the different elements and that and what it does. And one of the things that we want to talk a little bit about, and I've mentioned a little bit earlier, is about how radioactive particles that come off of these atoms as they have their radioactive decay, how they can penetrate things. And on the top of page 296 is a drawings of 4 different materials, and it has the 4 major particles that can come off of these radioactive decaying elements, and it shows how much they can penetrate. So the top one is the alpha particle, which is a helium nucleus without any electrons that breaks out and it goes flying along, and it's the heaviest and it's moving the slowest. And so as it moves away, it could be stopped by a piece of paper. That's what that's showing. You can see the green line and it stops at the piece of paper. Right below it is a beta particle, which is basically the equivalent of an electron gets kicked out and it breaks. It's not an electron off the surface, it's an electron that breaks out of the middle and comes out of a neutron, leaving a proton, and it shoots out. And it's moving faster, and it'll go through paper, but would be stopped by a piece of plywood or a thin sheet of metal or some kind of tin. The next one below that is gamma rays. And these gamma rays are moving at the speed of light. They're electromagnetic waves, and they have a super high frequency and a lot of energy, and they can penetrate through a lot. They penetrate right through your body. And they penetrate so much that they can penetrate through about 5 inches of lead or a couple of feet of packed earth or concrete. They can also penetrate through about 5 or 6 feet of water. I mean, they really can penetrate through a lot of things. If you look just underneath those pictures, you'll see table 17.4, and it kind of explains a lot of those. We get to the 4th particle, which is neutrinos, or the 4th thing that comes out is neutrinos, and they're really subparticles, and they come out, they're neutral, but they're really small, and they come zipping out, and they travel really fast. They don't travel quite as fast as the speed of light, but they still travel really fast because they're not interfering with anything. They shoot right through things, and I heard once before that they pretty much can shoot almost clear through the earth in certain places and that. They're almost impossible to stop. They can be kind of trapped, mostly detected, and they put these great big volumes of water, and they can detect the neutrinos going through them, and they put some cadmium and lead around it and everything else to try to slow them down, but they can be detected. Now, the next thing we want to talk about is what's known as a half-life. So we talked about the fact, like you take a uranium and it breaks apart, and as it breaks apart, it becomes a different element. Well, over time, more and more of those do that until eventually half of the volume completely converts to something else. Now, if that other stuff is radioactive as well, it'll continue to also have some kind of a half-life. If you look on table 17.4, which is just under the table 17.3 we were just talking about, there's a list of some half-lives. Now, if you look at uranium, which is the end one there, it says 4.51 times 10 to the 9th years. That's 4.5 billion years is its half-life. So if you had a chunk of uranium, after 4.5 billion years, half of it would have turned into other stuff and wouldn't be uranium anymore. Now, the easiest way to visualize this is by splitting it in half, but in reality it's intermixed all over, evenly dispersed all over half of it becomes. But we're going to draw a little cube here, and we're going to talk about carbon-14, which has a 5,730 year half-life, which is much, much faster. So we have this cube. It's pure carbon-14. And after 5,730 years, half of it isn't carbon-14 anymore. So we go like this. And we're going to delete that part, and we have half of it left is carbon-14. Now, in another 5,730 years, it goes through another half-life. It's not that the rest of the other half is gone in another 5,730 years. The activity slows down because there's less stuff around it to agitate it and everything, and so it takes longer and longer. So after another 5,730 years, we just have this quarter, so we have 1/4 of it is still carbon-14. And then again, if you go another 5,730 years, you'll lose another portion, another half. So all we have is this cube right here. And so that's the way half-life works. Now, here again, remember that it's all interdispersed all over and everything, but you get less and less and less of it. Now, and the less there is, the less agitation's going on, and the less it slows down its activity. Now, we use a lot of these different elements for all kinds of things for studying, scientific studies. There's the big CERN particle accelerator that we've talked about earlier in the year, where they will accelerate particles super fast to create and destroy. There's other ways by putting things in what's known as a breeder reactor, and they can cause all this agitation and control it in a way that they create other elements. And if you look on your periodic table at the end of your book, here is uranium, 92 protons, atomic weight of 238. That is the largest natural occurring element on Earth. All the ones that are larger, and this whole row up here, all the ones that are larger are man-made in some kind of reactor system or particle accelerator. They give them different names. This one right here, which has an atomic number of 94, is plutonium. It has a fairly long half-life, very similar in some ways to uranium. But some of these over here, like californium and things like that, have a shorter half-life. Some of those things are super, super expensive. Tens or hundreds of thousands of dollars an ounce. And they're named after some of the institutions that helped to create them, or after famous scientists and that. Those are kind of named after those because they're more modern day creations. But just remember that uranium is the largest one that occurs naturally on Earth. Now, one of the things that this radiation does is, because it can be damaging, it can get inside your body, it can shoot right through your body. Your gamma rays will go right through you, and as they go through, they can get into inner organs and your skin and different things like that, and they can change the characteristics of the actual atoms that are in there that are making up your body, and they can make you extremely sick from radiation poisoning if you get enough of it. Small amounts, usually your body can just replace as part of the natural flow of things. but when you get a large doses of it, can be quite damaging. And then there's a couple of things when it comes to, in the history of the world, when it comes to nuclear activity with regards to some of the weapons and that have been made in the past. During World War II, the United States dropped nuclear weapons, 2 of them, on Japan. Both of those were fission type bombs, where you had a large chunk of uranium, that there was enough of it that it had a critical mass, which caused it to go into self-explosion basically. And we'll discuss that more in next year's science class of physics, but it's breaking the uranium or plutonium atoms apart. It's fission, you're breaking them apart. Now, a more powerful one that was done later, that are known as H-bombs or things like that, they're fusion, and they use heavy hydrogen, and they get it accelerated and super excited through the use of a regular fission bomb that gets up to tens and hundreds of thousands of degrees, and it gets the hydrogen going so fast that they start smacking into each other and they create helium. And then it's a fusion because they're fusing together. They're going so fast that they get close to that point, and that strong force grabs them and holds them, and it gives off massive amounts of energy, much more energy than fusion does. And some of these things are, they're much more powerful than anything else that's out there, and they're super dangerous. And so anyway, that finishes this year's chemistry. To get credit for this lesson, there's a couple of things. One, I need you to text to me your name, and it needs to say that you finished watching, you watched the whole last lesson of chemistry. Then I will give you extra credit for this lesson. If you don't, I'm not going to give you a 0, but you might as well get the extra credit. So text me saying I watched the last of the last lesson where you asked me to send you the text message, and I will give you credit for that. Now, a couple other things. Tuesday is the last day that I will accept any of your previous assignments, the test, anything. If you want credit for that stuff to go towards your grade, to help you get a passing grade or to improve your grade, all of those things must be turned in by Tuesday. I will try to correct them Tuesday afternoon so that we can get everything finalized and everything graded. So, because of the fact that there's a lot of things going on, you probably want to do it as soon as possible. One other thing, you need to turn in your science books to Sister Sandra. So the chemistry books all need to get turned in as probably on Monday or Tuesday when you turn stuff in. This is the only thing that wouldn't require that, so you can turn in your book as soon as possible. If you see this video, because I'll be posting this video Monday morning super early. If you see it early enough to turn it in Monday, fine. If not, turn it in Tuesday. So we want everything done, turned in by Tuesday. Lastly, I want to thank you all for allowing me to teach you this year. I hope you had a good time and learned a bunch of stuff. Hopefully it can be useful to you in the future. All of those that are interested, next year we will be teaching physics, which gives you an understanding of a lot of what goes on around you. There's so much understanding of how life is, how things work. Chemistry works about the little in microscopic or even submicroscopic things like atoms and elements and stuff like that, where physics deals with more of the larger things for the most part. And it's really fun, it's really interesting, and I look forward to having you there. And hopefully we can get beyond all this and we can actually be in a classroom setting. So anyway, thank you once again, and don't forget to turn in everything by Tuesday. Thank you.